Hey there, it's Shannon Magic Myers, and today we will start exploring set theory. Very cool section, so let's just get to it. In this chapter, we focus more on the properties of sets in general than properties of the elements in the sets. All mathematical objects, even numbers, can be defined in terms of sets. And the language of set theory is used in every mathematical subject. So 6.1 goes through a bunch of definitions and the element method of proof for some property about a set. So let's check out what it means for a set A to be a subset of set B. So this symbol here represents subset. And if we look at it as a formal, universal, conditional statement, we have something along these lines. Some set A is a subset of set B if and only if for any x, if x is an element of A, then x is an element of B. Okay, so far? All right. Well, we've got an if-then statement. So what would the negation be? The negation would be beautiful, existential. So we would want to say what? So A is not a subset of B if and only if there exists some x, which is an element of that first set and not an element of the second set. So don't forget about De Morgan's laws, right? That's how you negate a conditional statement in if then. Cool. All right, beautiful. So next up, a proper subset is a subset that is not equal to its containing set. So a subset is always, or a set is always a subset of itself. So the proper subset doesn't include that. And one thing to note too is that the empty set is a subset of any set. All right. And we'll be talking about that a little bit later and even more in depth in a later section. All right, so A is a proper subset of B if and only if 1. First of all, A has to be a subset of B, right, in order to be a proper subset. And 2, there has to exist some x that is an element of B such that x is not an element of the set A. So that's that condition that makes it where it's not equal to its containing set. All right, so let's look at a couple of examples. So if A is the set 10 mod 7, and B is the set square root of 9, comma, 18 mod 5. Let's answer these questions, all right? So first of all, what are these sets? Well, what is 10 mod 7? It's the remainder you get when you divide 10 by 7, right? So A can also be written as the set that has the symbol 3 only as an element. And then B, well, the square root of 9 is what? Beautiful. 3 and 18 mod 5 is 3, but you don't have to repeat that element. So we would just list that element 3 once. Okay, so is A a subset of B? Well, yes, right, because every element that's in A is also in B, right? So that's a yes. Is B a subset of A? Yes, and you know what's we're gonna find out? We're gonna find out that A equals B because every element of A is also an element that's in B. But is A or B a proper subset of the other? No, because 3 is the containing set, and the only subset within either set is 3, right? So we would say no. Cool, cool? All right, so here we go. These can get a little bit confusing, but I think you'll understand them more when you look at power sets. So X is equal to the set of the set X, comma, the set Y, comma, the set Z. And Y is equal to X, comma, Y, comma, Z. So this one, it's a little tricky. Neither one is going to be a subset of the other because X is not the same as the set X, or the set that contains the symbol X. So X is a symbol, right? That's in Y, one of the elements of Y. But the set of X, or the set containing X, is an element that's in the set X. So they're not the same. And so since neither one is a subset of the other, they certainly cannot be a proper subset of the other. Cool, cool? All right. So when you want to do a proof, the element argument is something that is useful. So this is a basic method for proving that one set is a subset of another. So if you have some sets X and Y that are given, if you want to prove that X is a subset of Y, you suppose that X is an element of X, and then you want to show that that element X is also an element of the set Y. And then another definition. So given sets A and B, A equals B, written just A and the symbol equals and then B, if and only if every element of A is in B and every element of B is in A. So symbolically, A equals B if and only if A is a subset of B and B is a subset of A. So this one here, notice that these guys were each subsets of each other in example 1, and so therefore A was equal to B. Cool, cool? All right. So next up we have, I just wanted to kind of give you a visual here. So there's a couple different ways that A can be a subset of B. So if you've got, let's say that this is the set A, right? Or actually, we'll call this the set B. And we'll make 2 of them. So there's a couple different ways this can happen. And then let's say A, we've got completely contained in B like this. So that's one way to show a subset. Or A could equal B, right? And that would be, I'm meaning for this to go right on top of B. Right, so A equals B. And so these are 2 ways to show that A is a subset of B. And then coming over here, if we want to show that if, what it looks like if something is not a subset, Well, one way is you can have, your set B. Whoops. Your set B here. And then your set A, could be completely unattached, right? You could also have your set A intersect part of set B, but not be have it overlap, not be have all the same elements. Or you could have it where A was the containing set and B did not contain all the elements of A but was a subset. And so these are 3 different ways to show that A is not a subset of B. So there is this one, and then the third one. So 1, 2, and 3. Cool, cool? All right, so with example 3, now this one, it's going to take a little bit of of brain power, so you might want to pause the movie, get yourself some caffeine, make sure you're at the top of your game here. It's a little bit abstract, all right? So let's take a look. So basically, we've got these 3 sets, A, B, and C. And A is X that belongs to the integers such that, so your author uses the straight line for such that. I think the more modern thing is to use the colon. So whichever one you want to use, I understand both of them, okay? All right, so X is an integer such that X is equal to 5A plus 2 for some integer A, all right? And then the set B, Y is an integer such that Y is equal to 10B minus 3 for some integer B. And then C is equal to Z, which is an integer such that C is equal to 10C plus 7 for some integer C. We want to prove or disprove the following statements. So the first one would be A is a subset of B. Second one would be B is a subset of A. And then the third one would be that B equals C, which means that if we think that one's true, we have to show that, awesome, B is a subset of C and that C is a subset of B. So let's start with A. Okay, so now, there's infinitely many integers one could plug in, right? So let's go ahead and take a look at this. If we tried plugging in 0, in each case and see if we get a true statement at the end or a false statement at the end, that would give us sort of a starting point, right? So I will do that for A. So, or number 1 rather. So here, if we let A, not the set A, but the integer A, if we let that equal to 0, right? Well, looking at this first equation, we would have X is equal to 5 times 0 plus 2, right? Which is just 2. So I'm getting that over here. Cool, cool? Now what I want to do is I want to see, in order to show that A is a subset of B, every single element that's in A would have to also be in B, set B, right? So if I take a look and if I suppose that two is equal to 10B minus 3. So what the plan is here is I'm going over here and I know that the element 2 is in set A. So I'm going to check and see if the element 2 is in set B. And the trick with this one is that all of X, Y, Z, and A, B, and C are integers, right? So if I have that in here, all right, so I'm working with that equation here, and I'm taking this value that we got from setting A equal to 0. So this value 2 is something that X can take on a value of. Cool, cool? All right, so simplifying, what would I get? I would end up getting that 10B would equal to what? 5. Beautiful. So B would equal to 5/10, which is 1/2. But 1/2 is not an element of the integers, right? So therefore, we know that B has to be an integer, right? So therefore, what do we know? We know that the set A is not a subset of the set B, because when we took one of the elements that was in set A, right, and checked to see if it worked for set B, it did not. All right? Cool, cool? Very good. So we're done. A is not, a subset of B. Let's take a look at number 2. All right, so is B a subset of A? So let's try doing the same kind of thing, just a quick check to see if it works. So, I mean, keep in mind we're just, will it work, right? Well, I'm going to again try letting. So in this case, I need to find an element that's in the set B, and I need to see if it's also in set A. So I'm going to let B equal to 0 now. And so using that pink equation, do you see that? That means that y is going to be 10 times 0, which is 0, minus 3. So y would be negative 3. And then let's suppose that negative 3, our y value, was equal to what x is supposed to equal to, 5a plus 2. So now I'm working with this other equation here, right? And I want to see what I get. So, all right, let's see what happens. Well, 5a, this is a 5. 5a would end up being equal to, beautiful, negative 5. So a would be negative 1, which is an element of the integers, right? So we know that there's at least one element that's in set B that's also in set A. Good so far? Okay, so let's take a look. We now need to do this in general. So it is a proof. All right, so we're gonna start it out the same way, except now everything needs to be in general. So, you know, our evil plan is that we need to show that y is equal. I'm taking, you know, the equation that defines, you know, all the elements that are in A. So we need to show that y equals to 5 times some integer plus 2, because that is how set A, the elements in set A are defined. Okay? All right, so to set that up, let's see what we need to do. All right? So from our premise, okay, what do we know about y? Right? We know that y is equal to 10b minus 3, and b belongs to the integers. Okay, so far? So why don't we suppose that there's some a that exists, right, that belongs to the integers such that y is also equal to 5 times a plus 2. Okay, so far? All right. So, what should we do? Well, we have two expressions for y. So by substitution, we could say 10b minus 3 is equal to 5a plus 2. And that 10b minus 3 came from how y is defined. Cool so far? Awesome. And the 5a plus 2 came from how we defined y in terms of a. So what we want to do is we're going to kind of do a twofold thing. We want to isolate a, all right? And when we do that, we will then plug in what we got for a in terms of b into the original equation for a and show that it's equal to y, right? So let that kind of simmer for a second. And here we go. So doing some algebra, do you see we would have 5a is equal to 10b minus 5. So dividing everything by 5, a is equal to 2b minus 1, which belongs to the integers. Good so far? And let's see, what else do we know? We know for sure that y is 10b minus 3, correct? So we want to rework this situation where we get y is equal to 10b, where we get 10b minus 3, okay? Because we know that's in the set B. So let's see what we would get for 5a plus 2 if we substitute in 2b minus 1 for a. All right, so that would be 5 times 2b minus 1, which is the sum integer part, plus 2. Well, that's equal to 10b minus 5 plus 2, which is equal to 10b minus 3. But what is 10b minus 3? Beautiful. Y. So we're done. We've shown what we needed to show. Cool so far? All right. So what would we say here? Actually, let's say, finish it off, and we would say hence or therefore or whatever, B is a subset of A. Cool, cool? All right. So B equal to C. Well, again, if we sort of try it out, let's see what we would get. And so again, we're going to check. And let's go ahead and rewrite the equations up top so we have them. We know that y equals 10b minus 3, and we know z is equal to 10c plus 7. So when we check it out, right, if b equals 0, what happens? Y would equal to, beautiful, negative 3. And what would we do next? We would then see if we get an integer when we plug in y equal -3 in for some element that's in set C, which is the z equation. So we would say -3, we would let z take on that value of -3, set it equal to 10c plus 7. Well, that gives us that 10c is equal to -10. So c would equal to -1, which certainly is an element of the integers. So we think that by doing that work, we think that B is a subset of C. Set B is a subset of set C. Now let's check the other way. If C is 0, then Z is equal to, 7. And then we're going to let Y take on the value of 7 and see if we get an integer. So 10b minus 7 equal to 10b minus 3 would give us 10b is equal to 10, which would give us that b is equal to 1, which is an integer. So there's a good possibility that these two sets are equal, all right, subsets of each other. So like we were talking about earlier for our proof, we need to show two cases. We need to show that B is a subset of C, and then we also need to show that C is a subset of B in order to conclude that these sets are equal. So here we go. Proof. So part 1 of our proof, we need to show that what? So let's do let's show first that B is a subset of C, right? So we need to show that Y belongs to the set C. So Y would have to equal to 10 times some integer plus 7, because that's how the elements that are in set C are defined, okay? All right, so let's do it. What do we know about Y? We know that Y equals what? Beautiful. 10b minus 3. B belongs to the integers, right? And now suppose that there exists some C that belongs to the integers such that Y is also equal to, 10c plus 7. Good so far? So what will we have? We'll have 10b minus 3, using substitution, is equal to 10c plus 7. Working to isolate the term with C, we would have 10c is equal to 10b minus 10. And dividing through by 10, we would get C is equal to B minus 1. Well, B minus 1 through closure properties belongs to the integers, right? So now we need to show that, remember, 10 times some integer plus 7 is equal to Y, right? So let's do it. 10 times some integer, which is our B minus 1, right? Actually, I'll rewrite it. So 10 times C plus 7, substituting in this B minus 1 in for C, is equal to 10 times quantity B minus 1 plus 7, which is 10B minus 10 plus 7, which is 10B minus 3. But what is 10B minus 3? Beautiful. It's y, right? Because y, sorry, I forgot what color I used. Y is 10b minus 3. Cool, cool? All right. So B is a subset of C. And that part's done. So for part 2, what do we need to show? We're going to need to show that. So now we want to do that C is a subset of B. So we need to show that Z is equal to 10 times some integer minus 3, because that is what y is equal to, right? And over here, just so you know, that's why this expression was the expression all elements in set C have. All right, so, okay, well, what do we know this time? We know that Z is equal to what? Beautiful. 10C plus 7, where C belongs to the integers, right? So let's suppose that there exists some B, right, that belongs to the integers such that Z is also equal to 10b minus 3. So we want to show that some, all the elements that are in C are also in B. Okay? Set C and set B. All right. So here we go. By substituting, we'll have 10C plus 7 is equal to 10B minus 3, isolating the term with B because that's how the elements in set B are defined. We've got 10B is equal to 10C plus 10. So B is C plus 1 dividing out of 10, which is indeed part of the integers by closure. And so now, what do we want to do? We want to take the general form of B, right? So 10B minus 3, and we want to substitute in what we solved for, what we got for B in terms of C. So here, this is B. And we're going to go ahead and plug that in. And that gives us 10C plus 10 minus 3, which is 10C plus 7. But what is that? That is Z, right? All right. So what did we find out? So C is a subset of B. Therefore, B equals C. And we're done. Cool, cool? All right. Next up, we are going to define some operations on sets. So the union of A and B, denoted in this way, is the set of all elements that are in at least one of A or B. So union sets are usually larger. The intersection of A and B, denoted like this, is the set of all elements that are common 2A and B, so it's often a smaller set. All right, the difference of B minus A, also called the relative complement, of A and B, denoted like this, is the set of all elements that are in B and not A, right? And the complement of A, denoted like this, is the set of all elements in the universal set U that are not in A. So what we have going on is this. We have A union B is equal to the set X belongs to the universal such that X is an element of A or X is an element of B. A intersect B is equal to the set X belongs to the universal such that X is an element of A and X is an element of B. B minus A is equal to X belongs to the universal set such that X belongs to B and X does not belong to A. And A complement is equal to X belonging to the universal such that X does not belong to A. All right, so let's take a look at some pictures as to what this will look like. So if the whole square represents the universal set for each of these, I'll shade the regions. So if we've got set A and set B, so A and B, A and B, A and B, A and B. And I'll shade the regions that go with each one. So we'll have a union example, we'll have an intersection, we'll have a B minus A, and we'll have our A complement. All right, so for shading, I'll have A union B is going to be everything in A, you know, it's got to at least be in A or it's got to be in B, right? So that's the picture, that shaded region is the picture of the union. A intersect B is going to be, oops, didn't turn out very well. It's just going to be the overlapping part, the part in common. B minus A will be everything that's in B but not in A, so that relative complement of A and B, okay? And A complement will be anything that's not in A, so you'll have all of this stuff plus anything that's outside of B as well, as long as it's not in A. Okay, so the shaded regions represent models of each situation. Cool, cool? All right, and obviously we shouldn't have any, you know, anything outside. All right, so now let's check out the next example. So it's important that you understand, you know, your basic number sets. This fancy Q represents the set of rational numbers. And, you know, one way you can think of that is Q for quotient, right? Remember, a rational number is the quotient of two integers, two non-zero integers. Or where actually not two non-zero, where the denominator integer is not zero. So think about the positive integers. Are they a subset of the set of rational numbers? Yes, right? Because you can write all positive integers as a fraction. So this would be a yes, right? What about the set of negative or real numbers? Are they a subset of the rational numbers? No, because the real set of negative real numbers, right, includes stuff like negative root 2, right, belongs to the reals. And negative root 2 is not an element of the rational numbers, set of rational numbers, because it's irrational. Now, what about number 3? So this one would be false. So number 3 is the set of rational numbers a subset of the set of integers? Well, no, I mean, they have elements in common, but do you see that 1/2 is an element of the set of rational numbers, but 1/2 is not an element of the set of integers. So this would be a false statement. What about this one? Is the intersection of the set of negative integers and the set of positive integers equal to the empty set or the null set? That's what that 0 with the line through it means, empty or null set. You could also notate it with empty set brackets, but your author typically uses this one. So what do you think? Good. That is true, correct? Because they don't share any elements in common, right? What about the union of the negative integers and the positive integers? Is it equal to the set of integers? No, that's false. Why? Because 0, the element 0, is an element of the integers, but 0 is not an element of the negative integers. Well, I'll say and 0 is not an element of the positive integers. It would need to be an element of at least one of them for this to be a true statement. All right, how about the next one? Is the set of rational numbers union the set of integers equal to the set of rational numbers? True, yes. Okay, so next up, just some notation in case you forgot. The open interval from A to B is equal to X belongs to the real numbers. You need to say this such that A is less than X is less than B. So the endpoints are not included. Now over here is when you'd include A and not B. So X belongs to the real numbers such that A is less than or equal to X, which in turn is less than B. Coming back over here, we would have X belongs to the real numbers such that A is less than X is less than or equal to B. And then we'd have X belong to the reals such that A is less than or equal to X is less than or equal to B. So the endpoints are both included. All right, so remember infinity and or negative infinity, they are never, you never have brackets around that part of them because they just are, you know, a direction, right, that you'd be moving. So they're just kind of an idea, right? So in this case, infinity would be like infinitely to the right or infinitely to the left because we're talking about just the an x-axis, a horizontal axis, right? So, all right, so here we go. We've got, in this case, we'd have x belongs to the real numbers such that x is greater than a. And then below, we'd have x belongs to the real numbers such that x is greater than or equal to a because a is included. And then here we would have x belongs to the real numbers such that x is less than b. And then over here we'd have x belongs to the reals such that x is less than or equal to b. Cool, cool? All right, so now let's look at these sets x and y, all right? So let's also kind of take a picture, look at a picture of these two sets, all right? So okay, cool, cool. And so now let's take a look at these sets here. So if we do the set x and, you know, this purple, it goes from -3 inclusive, so I'm just going to do it as a closed circle, right, to 5 inclusive. And so that's what our set x looks like. Cool, cool? And our set y would look like this. So it would go from 0 inclusive, but then it wouldn't include 3. It would have like an open circle at 3. Cool, cool. All right, so what is the union of these two sets, x union y? Beautiful. X union y is happens to be equal to the closed interval from -3 to 5, right? But isn't that also equal to the set x? So just sort of keep that in mind, right? So this was officially the answer, but it was also equal to the set x, all right? How about x intersect y? Where do they overlap? Awesome. 0 inclusive to 3 non-inclusive. And so again, that's the official answer, but what is it also equal to? Beautiful, the set y. Are there any elements that are in y but not in x? No, right? Because x is the larger set. It's a containing set, right? So we would have the empty set, right? The null set. What about x complement? X complement would be beautiful. We would have minus infinity to -3 non-inclusive, so everything up to -3 coming from the left, union 5 non-inclusive to infinity. So everything outside of x is what we would get for x complement. All right? So everything outside of this purple set is what we got for the complement. All right, so that is that problem. Cool, cool. All right, now let's draw a Venn diagram to describe sets A, B, and C where A is a subset of B, C is a subset of B, and then the intersection of A and C is not empty, right? It's not the empty set. So let's draw our universal. So we're going to have 3 sets. So what's going to be the big set? Beautiful. The biggest set would be B, because both A and C are subsets of B. And we also want to be careful because we are drawing the intersection of A and C where it's not empty. So something like this would work, because as you see, there's some elements in the intersection. Cool, cool? All right. So here we go. Definition of unions and intersections of an index collection of sets. So here we go. Now there's, hopefully you can see it. There's set notation on the end of each of these. So basically the union from I equals 1 to n of AI is equal to X, which belongs to the universal set, such that X belongs to some AI for at least one I that goes from 0, 1, 2, all the way down to n. All right, so the infinite union of AI as I goes from 1 to infinity is going to be X belongs to the universal such that X belongs to AI for at least one non-negative integer I. Oh, and you know what? I'm sorry. The indices on this need to be from 0 on all of these. Okay, so the intersection from I equals 0 to n of A sub I is the set where X belongs to the universal such that X is an element of AI for all I equal to 0, 1, 2, all the way down to n. And then when you have an infinite intersection from starting at 0, it would be X belongs to the union such that X is an element of AI for all non-negative integers I. Okay? All right, 2 sets are called disjoint. If and only if they have no elements in common. Okay, so symbolically, A and B are disjoint if and only if A intersect B is equal to the null set or the empty set. All right, so sets A1, A2, A3, we have another definition, are mutually disjoint or pairwise disjoint. It's also called non-overlapping. If and only if no 2 sets, AI and A sub j with distinct subscripts have any elements in common. So more precisely, for all I and j equal to 1, 2, 3, all the way to infinity, AI intersect A sub j is equal to the empty set whenever I is not equal to j. Cool, cool. All right, so let's look at another example here. This one's kind of fun. So here we've got this partition going on, or not really a partition, but we have an index set. So the union of B1 to B4. And if we kind of take a look at what's going on here, let's see what we would have. I mean, if you have a number line and you're checking these out, we'd have something like this. Okay, so B1 would be equal to the set that goes from 0 inclusive to 1 inclusive, right? So you'd have 0 to 1. So that's what that one would look like. Cool, cool. And then if you took a look at, well, what's B2 equal to? Well, every one of them starts at 0. So it would go from 0 inclusive to 2. So I'm just plugging in a 2 for the I. And so you'd have this situation. And then continuing, we would have B3 would equal to 0 to 3 inclusive. And then B4 would be from 0 to 4 inclusive. All right, so here we go. So if I take a look at answering these, I'm looking at the union of all of them, that's going to be equal to the interval from what to what? Beautiful, from 0 to 4. And what is that also equal to? Awesome. Set B4, right? Okay, what about the intersection? Remember, they all intersected between 0 and 1 inclusive, right? And so their intersection would be this one here, the closed interval from 0 to 1, but then isn't that also equal to B1? All right. What about, are these four sets mutually disjoint? Well, no, right? Because they all intersect at least why don't we word it like this so it's better? I intersect on 0 to 1 at a minimum, meaning that some of them intersect on a longer interval, right? So none of the intersections are the empty set. So if you did it symbolically, the intersection of B1 and B2 is not equal to the empty set. Intersection of B1 intersect B3 is not equal to the empty set. B1 intersect B4 is not equal to the empty set. B2 intersect B3 is not equal to the empty set. B2 intersect B4 is not equal to the empty set, and B3 intersect B4 is not equal to the empty set. Cool, cool? All right. So now let's take a look at these guys here. So we've got, again, I is going from 1 to 4 in a couple of the situations. So let's take a look at what we've got. So here, we draw our number line. I guess we could draw our number line down here. And so if this is 1 and if this is 2, here would be about 4/3. About right here would be 3/2. And then about right here would be 5/4. So let's check out what our sets are. So our first set, R1, is going to equal to the interval from 1 inclusive to 1 plus 1/1, which is 1 to 2 inclusive. Good so far? All right, and then R2 is going to be 1 comma 1 plus 1/2, which is 1 to 3/2 inclusive. And then continuing, so it's similar to that last one. R3 is 1 to 1 plus 1/3, which is 1 comma 4/3. And then R4 would be 1 comma 1 plus 1/4, which is 1 comma 5/4 inclusive. All right, so again, we've got some overlap, and so here, let's see what's happening with the 4. So the union from I equals 1 to 4 of Ri, remember, is going to be R1 union R2 union R3 union R4, which in turn is equal to, very good, the interval from 1 to 2 inclusive, which happened to be the biggest set, which was R1. Good, good? All right, so now the intersection, or actually, let's go to from I equals 1 to n, right? So this would be, R1 union R2 union ... union Rn. Well, that one, what do you think it's going to be? It's still going to be R1. Why? Because, what do you think? The higher n gets, the smaller a chunk, right, of that interval it takes up. And so the largest set will be that first set. And actually, if we kind of take a look at number 5, and we evaluate the limit as I approaches infinity of the quantity 1 plus 1 over I, that's going to be equal to 1 plus 0, which is 1, right? So basically, what's going to happen is our largest set is going to be always that first set, R1, which happened to be equal to the interval from 1 to 2 inclusive, right? Whereas what's going to happen to the intersection? So the intersections, what's going to happen? Well, I mean, R1 intersect R2, intersect R3, intersect R4. Isn't that going to just be the interval from 1 to 5/4, right? Which was the pink one, so which is R4. Okay, well, as you know, did you notice that each one of these intervals got shorter and shorter as we got a bigger number? And so here, I mean, this would be R1 intersect R2 intersect dot 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 intersect RN. So what do you think is going to happen? Beautiful. We're just going to get RN for our intersection. Now, as I goes to infinity, right, what's going to happen to that intersection? I mean, isn't it going to get tinier and tinier and tinier and tinier and tinier, right? So basically, we know one thing for sure, though. Beautiful. We know that they intersect at 1, don't they? Because 1 was inclusive, right? So that's what's going to happen as I tends towards infinity. All right? Are these guys mutually disjoint? No, because isn't 1 is included in the intersection of each of them, right? All right, good so far? Okay, very good. So another definition, a finite or infinite collection of non-empty sets, A1, A2, A3, all the way down, is a partition of a set A if and only if A is the union of all of the AIs and the sets A1, A2, A3 are mutually disjoint. Okay. All right, so let E be the set of even integers and let O be the set of odd integers. So is the set E comma O a partition of the set of integers? Well, what do we know? Didn't we learn that all integers are either even or odd, right? And then remember, if you're wondering about 0, right? 0 equals 2 times 0, right? So 0 would be considered even, wouldn't it? Cool. All right, so here we have another definition given a set A. The power set of A, denoted, there's different ways to denote it. Your author had a different symbol, but I didn't have that one in my program that I could find, so I'm doing it with this one here. So we'll call it P at A, or power at A, is the set of all subsets of A. And we'll do an example of that in a moment. And another definition, let n be a positive integer and let x1, x2, down to xn be not necessarily distinct elements The ordered n-tuple x1, x2, down to xn consists of x1, x2, down to xn together with the order. First x1, then x2 until you get down to xn. So an ordered two-tuple is called an ordered pair. And an ordered, three-tuple is called an ordered triple. So like if you haven't taken linear algebra yet, you see a lot of this notation because you go into n space. So, you know, there's just not enough letters to name them X, Y, Z, W, etc. So they just go X sub 1, X sub 2, all the way down to X sub n. All right, so two ordered n-tuples. X1, X2, down to X sub n. And call it Y1, Y2, down to Y sub n are equal if and only if x1 equals y1, x2 equals y2, etc., down to xn equals yn. So symbolically, x1, x2, down to xn equals y1, y2, down to yn if and only if x1 equals y1, x2 equals y2, all the way down to xn equals yn. And then in particular, if you've got, say, two ordered pairs, AB equals CD if and only if A equals C and B equals D. Okay? All right. Another definition. So given sets A1, A2, A3, all the way down to A sub n, the Cartesian product of A1, A2, A3, all the way down to AN, denoted like such, is the set of all ordered n-tuples, A1, A2, all the way down to AN, where A1 is an element of capital A1, A2 is an element of capital A2, all the way down to A sub n is an element of capital A sub n. So symbolically, the Cartesian product of A1 down to AN equals this set. Now this set is in the form of an n-tuple all the way down to AN, such that A1 belongs to capital A1, A2 belongs to capital A2, all the way down to AN belongs to capital AN. In particular, A1, the Cartesian product of A1 and A2 is equal to A1, A2, such that A1 belongs to A1 and A2 belongs to capital A2 is the Cartesian product of A1 and A2. Okay, so example 10 kind of brings a lot of this stuff together. So if A is the set 7, 9, and B is the set 9, 19, please compute the following. All right, so we're going to find the power set of A intersect B. Okay, well, what is A intersect B, right? Well, this would equal to what? The power set of, so what is the intersection? Beautiful, it's just 9, right? So what are all the possible subsets of 9? Well, remember how we were saying that you're always going to have the empty set is a subset, and we'll get to that in a later section in more depth. And then a set is always a subset of itself, right? And so those are all the possible subsets of the set 9 that contains 9. Good so far? All right. What about the power set of A? So that's all the subsets of our set A, which consisted of the elements 7 and 9. So this would be equal to all the possible sets of the set 7, 9, which is, well, don't forget about your empty set. So it could be the empty set. It could be each of the set of each of the elements alone. Or it could be the set itself. Cool, cool? All right. Okay, next up, the union. So the union, all the possible sets, so the power set of the union is going to be, the union of A and B is what? So 7, 9, and 19 is the union set. So that's going to equal to, remember, you're always going to have your empty set, and then what? You can have each of them alone as a set. And then what? They could be 2 at a time, right? So 7 and 9, 7 and 19, and then what would it be? We'd have to include 9 and 19. Cool, cool. So that's all of them, all the possible ways to do 2 at a time. And then it could be the set itself, right? So we have 7, 9, and 19. And that's all in a set. Cool? All right, now, here we go. The power set of the Cartesian product of A and B. So, let's see what we've got. The power set of the Cartesian product would be, now we're going to have a set of ordered pairs. All right, so all the Cartesian product itself is going to be the ordered pair 7 and then 9. So the 9 is from set B and the 7 is from set A. And then 7 and 19. All right, so now we're going to work with the 9 from set A. So then we'll have 9, 9. And then what? We'll have 9 and 19. Cool, cool? So you can get 4 ordered pairs out of that. All right, well, now you've got, you need to find all the possible subsets of these 4 sets. So, and remember, each set is in the form of an ordered pair. So, here we go. And I just want you to, since we hadn't done the Cartesian product before, I want you to see that the Cartesian product is this result here. And now what we're going to do is we're going to evaluate all possible subsets, the power set. So remember to start with our empty set, and then we can do the set of each ordered pair alone. Okay, so we've represented each ordered pair alone. Now we need to move into pairs of ordered pairs, right? Or sets of two ordered pairs. So continuing, we'll have, I'll do 7 and 9 first with each one. So 7, 9, comma, the ordered pair 7, 19 as a set. 7, 9, and then the ordered pair 9, 9. 7, 9, and then the ordered pair 9, 19. All right. And now I need to do what? Let's start with 7, 19. So 7, 19, and then 9, 9. 7, 19, and 9, 19. And then what? 9, 9, and 7, 19. Whoops. Okay, getting closer. All right, so that I believe that's all the ways that we can represent the 4 ordered pairs 2 at a time. Okay. Okay. Now we need to do them 3 at a time. So starting again with 7, 19, I'll do starting with 7, 9. We'll do 7, 9, and then 7, 19, and 9, 9. 7, 9. 9, 9, and 9, 19. There's one more way I can include 7, 9 in there. 7, 9, 7, 19, and then 9, 19. All right, and then starting with 7, 19, we'll have 9, 9, and then 9, 19. And then we can do the set itself, which was 7, 9, 7, 19, 9, 9, and 9, 19. Cool, cool? And then you close the set because remember the power set is a set itself. So it's got all these sets inside. All right, so the power set of the Cartesian product of sets A and B is all this here. Cool, cool? All right, so that is that one. And notice that even and odd integers are disjoint. They don't have any elements in common. All right, so that's it for today. We finished. So I hope you have a wonderful morning, afternoon, or evening. And please subscribe to help support my channel if you like what I'm doing. Bye.